All right, guys, so let's start. Okay. So first, before the start of your lecture, okay, just keep in mind, quiz 3 will be tonight. Okay, so quiz 3 mainly cover chapter 11, additional chapters. Okay, and so if the question didn't ask you anything, okay, so I didn't ask you kind of showed stair country or showed kind of the Cairo center with full bound whatever. Okay, so you don't need to show the wedge bound. Okay, just directly use the straight line. Okay, show the kind of reaction product. That's it. Okay, don't show kind of any intantimer or diastamer whatever. Okay, just show one product. Okay. But if the question asks you kind of show the stair country, okay, and then you need show the kind of wedge bound dash bound, okay, and then may ask kind of show more than one product and ask you their kind of relationship, okay. So that's the be careful, okay. Yeah, so I have kind of the office hour after the today's class, okay, from 4 to 5, okay. So if you have any question about the online homework or the agricultural homework or anything, okay, so you can just stay on kind of this lecture, okay, after the stay on kind of the Zoom, okay, after the lecture, okay. And a lot of students ask me kind of what kind of mechanism you need memorize, okay, so for the chapter 11, okay, so the 3 additional reaction, okay, so that's you have to the 3 mechanism, okay, mechanism 1 and mechanism 2 and 3, okay, so those you have to memorize, okay, so don't forget, okay. Other like the oxidation reaction, reduction reaction, something that's not required, okay, so that's just keep in mind, okay. Right, again, okay, so I have the actual office hours, okay, so just after this class, okay, so if you have any question, okay, and you can ask me, okay. All right, and then today we continue with chapter 17, okay, so aromatic reactions, okay. So last year the Friday we talked kind of the 4 ES reaction, okay. So last one kind of Friedel-Crafts accumulation reactions, okay. So for this reaction there are some kind of problem, okay. So first kind of the multiple the accumulation, okay. So what's that mean? Okay, so that's similar like the multiple accumulation for the amine, okay, we learned before, okay. So if you kind of the benzene, okay, and then you try to react only one equivalent kind of alkyl halide, okay, and then aluminum chloride as the catalyst, okay. So even one equivalent, okay, you can get kind of the mono substitute product, okay, and then di substitute product, and then tri substitute product, and even more, okay. So that's we call it kind of the multiple accumulation, okay. So it's hard to control only add one alkyl group on, okay. And why is that? Okay, because alkyl group we call it kind of the activity group, okay, and then kind of don't electron into the benzene ring, okay, make the benzene more reactive, okay. And if you don't understand this part, don't worry, okay. So we will talk about this one quickly, okay. So Right. Second problem we already talked about, okay, because the Friedel-Crafts accumulation involves kind of have carbon cation as intermediate, okay. So in this case, any reaction involves carbon cation as intermediate, okay. So we're trying to kind of there's kind of possibility for rearrangement, okay. So that's we already learned that, okay. So and the third problem kind of if there's electron withdrawing group, okay. So in this chapter, normally we call them kind of the deactive group, okay, already on the benzene ring, okay. That's will kind of deactivate kind of the benzene and then cannot do any kind of Friedel-Crafts activation, okay. So what's that mean, okay? All right, so there's kind of already has kind of electron withdrawing group, okay. All right, electron withdrawing group, okay. So deactivating group, okay, so pretty much or electron withdrawing group, okay. So later explain kind of it, okay. Right. And then if you want to do kind of Friedel-Crafts kind of accumulation reactions, okay. Just one. All right. So no reaction, okay. Yeah. So that's something keep in mind, okay. And so what's the deactivating group or kind of electron withdrawing group? Let's show here some example, okay. So pretty much a carbonyl compound and also kind of the center atom surrounded by some kind of the strong electron withdrawing group, okay, or kind of strong kind of the electron negativity atoms, okay. also kind of yeah, positive charge kind of yeah, cation. Okay. So about kind of electron yeah, deactivating group okay, and also kind of yeah, activating group I'll talk about soon. Okay. Right. So because of this yeah, limitation, okay, actually kind of yeah, free craft accumulation kind of yeah, is the least useful kind of yeah, the ES reaction. Okay. So yeah, we learned 5 ES reaction kind of yeah, free craft accumulations kind of yeah, not so common use kind of in the synthesis of the alkyl group substitute the bonding. Okay. Yeah, the reason showed here. Okay. All right. And then we will learn the last kind of the free craft kind of last ES reaction. Okay. So that's here the free craft kind of the acylation reaction. Okay. IFC. Some last question. Both okay. So both here the CX3 and those here the chlorine bromine are the electron withdrawing group. Okay. Yeah. The active group will also say that. Okay. All right. Okay. So yeah, for the FC kind of the acylation reaction. Okay. Pretty much the general reaction I show you guys. Okay. So there kind of bonding. Okay. And then yeah, you have kind of acid chloride. Okay. Also called kind of acyl chloride. Okay. And then again we use the aluminum chloride. Okay. As the catalyst. Okay. So after reaction is done. Okay. So we put acyl group. Okay. So yeah. So this part. Okay. Onto benzene ring. Okay. And so another byproduct kind of you don't need to show in kind of exam quiz HCl. Okay, so yeah. All right, and then for this reaction, okay, so the mechanism, okay, actually kind of all go by through kind of we call the acylium kind of the cation. Okay, so we remember okay for the free crack acylation or kind of whatever kind of ES reaction. So the casing how do we generate kind of kind of electron files. Okay, and then pretty much the same thing. Okay, so here I show you guys kind of the electron mechanism. Okay. Right, again, we have kind of aluminum chloride as starting material, okay, the catalyst, okay, and then you have kind of acyl chloride here, okay. Right. So for the acyl chloride, okay, so the lone pair electron fill in kind of the aluminum chloride kind of empty p orbitals, okay, and then you generate kind of this guy. Right. Right, and then forwarding okay, just kind of shift the electrons, okay. So yeah, okay, give electron to the chloride, okay. And then you generate kind of acyl chloride, okay. We call the acylium kind of the cation, okay. So this is the real the electron file, okay. And then to react with kind of bending, okay. Right. And then so falling kind of pretty similar like the other the ES reactions, okay. Right. So I shifted the acyl to another part, okay. And then next kind of this part, okay, coming, okay. Okay. So the CL-AL bond break up, okay, and then pick up the hydrogen, okay, on the intermediate, okay. And then go back, okay. That's here the give you kind of the aromatic ring, okay. Okay. And after reaction, okay, so you generate kind of HCl as a one product, okay, and then aluminum chloride, okay, as the catalyst, okay. That can be reused, okay. So yeah, this here just here can be recycled, okay. And for this reaction, okay, so the advantage is kind of no arrangement, okay. So that's different from kind of the acyl, the free crack kind of accumulation, okay. So because there's a free calculation, you generate kind of a carbon-cation intermediate. Okay? So otherwise you have kind of carbon-cation, there's kind of rearrangement possibility. Okay? But here we have kind of a different cation as an intermediate. Okay? So that's there will be no such kind of arrangement. Okay? Second, kind of because there's this acyl group kind of we call it deactivating group. Okay? And then there's kind of no multiple kind of acylation. Okay? So that's the good thing. Okay? And then only a thing, the drawback of the free calculation, same as kind of free acylation, kind of if there's kind of deactive group, okay, so you cannot do any kind of the acylation reactions, okay. So yeah, similar here, okay. So yeah, electron withdrawing group, okay. If you want to do kind of free kind of the acylation, also yeah, cannot work, okay. Yeah, no reaction, okay. Okay, and then for this reaction, okay, couple of things keep in mind, okay. The first kind of make sure that just the water free, okay. Okay. The reason for that kind of both acid chloride, okay. So yeah, and those animal chloride can react with water, okay. So acid chloride can react with water, you generate kind of the capsic acid, okay. So that's just the simultaneous reactions, okay, because this one kind of two reactive, okay. So once reaction is done, okay, so you just kind of capsic acid and then HCl, okay. And so similar thing kind of the acid aluminum chloride, okay. So yeah, that's if you react with water, okay, also just kind of quickly decompose kind of into the aluminum the hydroxide, okay, and then HCl, okay. Yeah, 3HCl. And so this week lab, okay, so we'll do kind of the free acylation reactions, okay. So if you already did the pre-lab, okay. So in the pre-lab, I emphasize kind of the absolutely no water in your glassware, okay. The reason for that is that's these two by the side reactions, okay. So if you are going to the any tiny amount of water will kill all the region, okay, and pretty much you will get kind of very poor yield, okay. So that's something keep in mind, okay. So make sure no water, okay. Yeah. Even you cannot use some kind of acetone, okay, so to clean your glassware because the acetone has a little bit of water inside, okay. And then second thing kind of not only the acyl kind of chloride as a reagent, okay, you can also use anhydride, okay. Also can be used as kind of the free kind of acylation reactions, okay. So yeah. Yeah, that's anhydride, okay. All right, give you one example, okay. And then you still can use kind of the aluminum chloride as kind of catalyst, okay. Right. So for this reaction case, so pretty much this one called kind of naphthalene, okay. Naphthalene kind of the later this chapter will list about the substitution reaction, okay. So the substitution always happen kind of these four positions, okay. Right. So once reaction is done, okay. So you add kind of the acetate group, okay, onto this naphthalene with called kind of the naphthalene case. So actually kind of this part, okay. And so for FC the acylation reaction actually quite often use kind of the intramolecular reactions, okay. So that's the probably that's right. I have one example here, okay. Right. So that's CR, okay. So this part actually kind of you see kind of long carbon chain linked two functional group, one benzene, one kind of acid chloride. Okay, so whenever I said kind of there's kind of the long carbon linked ones and two functional group. Okay, there's possibility kind of you have kind of ring closing reactions. Okay, right. And then we still use the aluminum chloride okay, as the catalyst. Okay, once reaction is done. Okay, yeah, that's the final product. Okay, pretty easy reaction. Okay. Okay, so now we move to a little bit the hard part for this chapter. Okay, so the effect of substituents. Okay, so what's that mean? Okay, so that means kind of if you already have one kind of substituent group under the benzene ring, okay, and then you try to do the second kind of ES reactions. Okay, how the reactivities? Okay, so maybe okay. Right, so we already have kind of one substituent group on the benzene ring, okay, and then we try to do the second EAS reactions, okay, all right, and then we compare with kind of just the benzene, okay, so there's nothing under the benzene ring, okay, right, and then first kind of the reactivity, okay, so how fast of this reaction okay compare with kind of benzene, okay, so the faster than benzene or kind of slower than benzene, okay, so that's kind of reactivity, okay. Reactivity kind of determined by the inductive effect, okay. And then second is kind of the relative the positions, okay, for the second kind of the substituent group, okay, second kind of electron file, okay. So for this already has one substituent group one, okay. So there are kind of in this case for this the substrate okay, there are kind of two also okay, that's also okay. And the two para positions, okay, para, okay, and then one actually kind of two meta, okay, sorry, so two meta and then one para, okay. Right. So in this case, there are kind of three possible products, okay. So one's kind of the also substitute kind of product, okay, goes kind of also position, either one is fine, okay. Another one's kind of the goes kind of meta position, okay, and then last one goes kind of the para position, okay, yeah. And so for the reality case, so if there's no residual selectivity, no kind of the residual chemistry, okay, so you should get all these the three products, okay. But for reality case, so only two possibilities, okay. Either get kind of the also or para kind of the disubstitute product, or you get kind of meta substitute product, okay. So that's the kind of the kind of relative kind of hard part of this chapter kind of we call kind of residual selectivities, okay. All right, so we do the one by one, okay? Yeah, that's one example showed here, okay. So we try to do kind of the nitration reaction to kind of toluene. Okay. Toluene already has kind of the benzene methyl group, okay, on kind of benzene, okay. And then you try to do it, okay. So the three possible product, okay. So the also meta and also para, okay. And theoretically speaking, if there's no selectivity, okay, you should get kind of 2, 2, 2, 2, 1, okay, because there are kind of two also, two meta, only one para, okay. But for the reality case, so we get 60% kind of the also product, okay, and then 37% kind of the para product, okay, so almost no meta product, okay. So that means kind of the methyl group actually kind of directing the nitro group, okay, into its also and then para positions, okay. And also if we compare kind of the toluene kind of the ES reaction with the just benzene, okay, the 17 times faster, okay. So that means kind of the methyl group actually kind of we call the active group, okay, make the benzene more active, okay. All right, so we'll study kind of reactivity and those residual selectivity kind of one by one, okay. First kind of the reactivities, okay. All right, so that's here comes kind of the electron donating group and the electron withdrawing group and also the activity group and also the deactivity group, okay. So so this the substituent group, okay, so really determine kind of how good of the benzene ring, okay. So if you have kind of electron donating group, okay, it will donate electrons into benzene ring, okay, and then make the benzene more electron rich, okay. electron more rich kind of the either carry kind of EAS reaction. So remember this chapter we learned reaction called kind of electrophilic kind of the aromatic substitution reactions. Okay, so more electrons at better reactivity. But on the other hand, okay, so if you kind of electron withdrawing group on the bending, okay, take electron away from kind of bending and then make make bending ring kind of pulling electrons and then not favor for kind of EAS reactions. Okay, so that's also showed here. Okay. So pretty much the electron donor group okay, so make the bending ring more reactive okay, and then faster the reaction rate okay, and then electron withdrawing group okay, slow down reactions okay, and then just kind of the just opposite kind of trend okay. Right, and then that's also just kind of just this, what I see kind of already also summarized here. Okay, increase the electron density in the bending case. So for the electron donor group, okay, and then faster reactions, okay, and the electron withdrawing group, okay, decrease the electron density, okay, and then slow down the reaction for the kind of the electron fire attack, okay. And overall, okay, so for you guys, just keep in mind, okay, so the compare each kind of just nothing on the bending, okay. Donor group increase the reaction rate, and then electron withdrawing group slow down the reaction rate. Okay. And in this case, pretty much we can see kind of if it's kind of electron the donating group, okay. And then people also call this kind of activating group. Okay. In the kind of EAS reactions, okay. And if it's kind of electron withdrawing group, okay, pretty much people also call kind of electron deactivating group, okay. So that's you can just goes kind of this through, okay, and then for the donating group, okay, definitely kind of increase the reaction rate, okay. Electron withdrawing group decrease the reaction rate, okay. All right. So now come the question, okay. So what group is kind of our electron donating group, okay, and what group kind of electron withdrawing group, okay. So that's here. And here's kind of the chart, okay. So show the all the most of it kind of electron donating group, okay. And then so actually kind of you can see kind of there are three categories, okay. One's kind of strong activating case, strongly activating case. So amine and also kind of the alcohol kind of oxygen kind of for group, okay. So all those kind of the acting group has kind of the lone pair electrons, okay. Lone pair electrons attach kind of the center atoms, okay. So can donate electron into the bending, okay. And then next category is kind of moderately kind of the activating group, okay. Moderately active group pretty much kind of amide and those the ester, okay. So keep in mind, okay. So you have to make sure that the for amide ester, okay. So the nitrogen or oxygen attached to kind of the bending ring, okay. So not another part, okay. So for this two, okay, because there are kind of the carbonyl group attached, okay, make the nitrogen and also oxygen not so strong the electron donating, okay. So compare is kind of the category 1, okay. Answer the yes, okay. So you have memorized this chart, okay. That's kind of the key kind of the knowledge for this chapter, okay. So actually not hard to memorize, okay. So as long as kind of find kind of lone pair electrons on the center atoms, okay, that's that should be kind of activating group, okay. And then second category kind of just lone pair electrons center atom kind of attach kind of carbonyl group, okay. And then the third category kind of we call it weakly activating group, okay. So this just two, okay. So one's kind of active group, one kind of bending, okay. So why they are weakly activating, okay? Because they can somehow kind of form hyperconjugation with the bending ring, okay? So remember we learned in the previous chapter, okay? So the carbon cation stability, okay? So tertiary more stable than secondary, and then more stable than kind of primary, okay? Reason for that kind of the sigma bond and the bending, okay? Okay, sorry, my powers run out. All right, 1 second, okay. 1 minute to get my power line, sorry. Sorry, my laptop run out of the power. Okay. All right, let's continue. Okay. All right, and so for the RQ group and also the benzene aromatic compound. Okay, so somehow you can donate electrons. Okay, into benzene, make kind of the electron more rich. Okay, so that's here we call kind of weakly activating group. Okay. All right, next the group is kind of electron withdrawing group. Okay, so yeah, still we have 3 categories. Okay, the first one is the halide. Okay, so the fluorine, chlorine, bromine, iodine. Okay, so that's a weakly deactivating group. Okay, and then second one kind of carbonyl compound. Okay, like ketone, aldehyde, carboxylic acid, ester, and also the amide. Okay, so that's the we call kind of moderately deactivating group. Here you need to be careful. Okay. For ester, okay. Ester, okay. So you have to make sure that the which end connect to kind of benzene. Okay. So if you have oxygen, okay, this end connect to the benzene. Okay. That will be kind of the activating group. Okay. So yeah. Right. But if it's kind of a carbonyl group, okay, this end connect to kind of benzene. Okay. Then that will be kind of the deactivating group. Okay. All right. So that's the need to be careful. Okay. So a lot of students kind of make a mistake. Okay. So just think out kind of answer. Okay. So either the activating or maybe just kind of only the deactivating. Okay. So you have to look at which end. Okay. Similar thing for the kind of amide. Okay. Right. So you have to look at which end. Okay. So if you have the nitro end connect with kind of benzene. Okay. So that's the activating. Okay. Right. So if you have the carbonyl end connect with benzene, kind of deactivating. Okay. Yeah, that's something need to be careful. Okay, so yeah, right. So that's also showed here. Okay, so yeah, amide ester. Okay, and then amide ester. Okay, so you have to look at kind of which end. Okay, and the last category is kind of the strongly kind of deactivating group. Okay, so for this category. Okay, so yeah, pretty much just some kind of center atom surrounded by kind of strongly electron withdrawing group. Okay, and also we also call them kind of strongly kind of the electronegativity atoms. Okay, or some kind of the negative positive charge kind of species. Okay, so that's please keep in mind. Okay, yeah, right. And here we just go back to explain. Okay, so we learned the 5 EAS reactions. Okay, why only the free cracker activation reactions kind of generate kind of multiple products. Okay, the reason for that all other 4 EAS reaction. Okay, only put kind of the acting group on the benzene ring. Okay, so no matter kind of nitration. Okay, sulfonation, bromination, chlorination, or kind of the free cracker acylation reactions. Okay. Or the acting group. Okay, so you can find them here. Okay, yeah. So in this case, yeah, if you put the deactive group on the benzene ring, okay, and then make the benzene last reactive, and in this case, yeah, you cannot put the second one on, okay. So we are the benzene kind of deactive. Only exceptions kind of require kind of the alkylation reactions, okay. So this one, okay, you put alkyl group on the benzene, okay. Alkyl group kind of the activating group, okay. So make the benzene more reactive, okay, and then more reactive, and then cannot stop, yeah, at this stage, okay, and go ahead and put the second one and third one on even more, okay. So yeah, so that's why you generate kind of multiple alkylation product, okay. So that's the explain the why the has kind of that's problem for the free alkylation reactions, okay. All right, so now we move to the probably most difficult part for this chapter, okay. So yeah, the residual chemistry of the multiple ES reactions, okay. So yeah, if you fall in sleep, okay, a little bit wake up, okay, or drink some kind of coffee, okay. So that's the kind of casing, okay. So yeah. All right. Okay, so yeah, like I said, okay, so yeah, the first substitute group on the benzene, okay, we determine kind of the position of your second substitute group, okay, either ortho, meta, or para, okay, and if there are kind of no selectivities, okay, so yeah, you should get kind of all three products in 2, 2, 2, 2, 1, okay, because there are kind of 2 ortho and then 2 meta and then only 1 para, okay, and but for the reality, okay. Only 2 kinds of directing effect. Okay, one kind of we called ortho para director, and another called kind of meta director. Okay, so that means kind of the group already on benzene can either directly kind of the second electron find on kind of ortho para position or kind of directly to kind of meta positions. Okay, so yeah. All right, so why is that case where let's see, relate to kind of reaction structure and also the electron donating, electron withdrawing group. Okay, so so we use kind of one as kind of example. Okay. Okay, so the phenol example. Okay. Right, so yeah, if we want to do kind of the ES reaction, okay, so for example, nitration reaction for the kind of the phenol, okay. Right, and then when you open it, okay, so yeah, probably we do like this way, the better, okay. Right, so the open kind of the one of the C theta bond, okay. Right. So I just ignore the hydrogen here, okay. So keep in mind there's hydrogen, okay. Right. So that's the one kind of resonance structures for the intermediate, okay. And then you can shift it here, okay. And then generate kind of second one, okay. And then now the content here, okay. Right. And then you can further shift these 2 pi electrons here onto here, okay, and then you generate kind of the third resonance structure, okay. Right. So for the third resonance structure, you can see clearly, okay, so the positive charge on the carbon with the OH group attached, okay. So OH group itself is kind of electron donating group, okay. So we already learned the case, also called activating group, okay. And then there's kind of lone pair electrons, okay, on the oxygen, okay, can donate electron into kind of this the bond, okay, and then you generate kind of the cation, and then the fourth one, okay. Right. And actually, the reality is the cation kind of the very stable, okay. Okay, reason for that kind of all 4 kind of the resonance structure, okay. Only this one kind of the follow octet, okay. All atom kind of has the either 8 or 2 electrons strong the kind of the center the atom, okay. Other has maybe kind of 6, okay. Right. And the similar thing, okay. So yeah, if we do the kind of para substitute kind of the product for this the nitration reactions, okay. So we open this double bond, okay. And then, yeah, we generate kind of a para product, okay. Okay, we open like this way, okay. Okay, positive charge will be here, okay. And then we can go ahead and shift the electrons, okay. So yeah, now we shift here. Okay, so you can see, okay, so we have kind of the positive charge, okay, onto the carbon with the oxygen attached, okay. So in this case, yeah, the similar to the top situation, okay. Yeah, we can draw one resonance structure, something like this, okay. Okay, and certainly, okay, so you can the shift the electrons, okay, like this, okay, this, yeah, the pi bond, okay, shift to between these two carbons, okay. Yeah, so here goes here, okay, and then no positive charge here. Okay. Okay, and then you can continue shift, okay, so yeah, just go roll around, okay, so yeah, this one go here, and then positive charge go back to here, okay. So in this case, yeah, for the para substitute kind of the reaction, okay, so we also can generate kind of one stable intermediate, okay, so this guy, okay, all right, and if we kind of further draw the meta, okay, so yeah, the substitute kind of situation, okay, so that will be a different story, okay. Right, so now we open the ring like this, okay, so yeah, pick up the NO2 plus, okay. Right, generate kind of meta substitute kind of product, okay. So we open the bond like this, okay. Right, and then yeah, you can go ahead and shift the pi bond, okay. Right, and also yeah, shift to here, okay. And then draw it here. Right, and then you can continue the shift it down, okay. So yeah, this one can going down or whatever, okay. So yeah, for the meta substitute situation, okay, you find kind of only 3 resonance structure, okay. So this is the also, okay. This is the para, this is the meta, okay. Right, so compare there kind of the resonance, you find kind of the also para get more resonance structures, okay. So each has 4, okay, 4, okay. But here the meta only 3, okay. So yeah, in the organic chemistry 1, we learned kind of more resonance structure, more kind of higher stabilities, okay. And also for the also para, okay, both have kind of the very stable kind of the resonance structures, okay. So that's here the okay. You can have kind of positive charge kind of on the oxygen kind of or maybe some kind of the electron donate group attached carbon, okay. So that's kind of further kind of the delocalizes positive charge into kind of heavier atoms, okay. So yeah, okay, here, okay, and then that's make it the all thing kind of more stable, okay. Right, so that's explain kind of if you have kind of electron donate group, okay, we also call it an activity group, okay, actually kind of the increase the also para kind of the stabilities, okay, and then increase kind of the reaction rate, okay. But for the meta, okay, so this positive charge bypass this carbon, okay, so the carbon with the OH group attached, okay, so that you cannot gain this kind of stabilities, okay, right. And so that's show the bunch of the pair, some here, okay. And for you guys, okay, that's the remember, okay, so maybe write it down, okay. So pretty much, if we are kind of electron donate group, okay, also called kind of activity group, okay, and plus, okay, halogen, okay. Just kind of chloride, bromide, iodide, or kind of fluoride, okay. Those will be kind of also para director, okay. Okay. And so on the other hand, okay, so if it's kind of the electron withdrawing group, okay. And then minus kind of remove kind of all the halogens, okay, halogen here, okay. That will be meta directors, okay. Okay, so that's something keep in mind, okay. And then I'll explain kind of further, okay. So why the electron withdrawing group, okay, also called kind of deacting group, okay. So kind of the meta directors, okay. So that's I have to kind of draw the kind of resonance structures, okay. Right. So this time I use nitrobenzene, okay, and still use the double bond one, okay. Right. So nitrobenzene, nitrous group, we already know that kind of the electron withdrawing group deactivating, okay. So we try to do the second kind of nitration reactions, okay. Right. So we try to draw the kind of the also product, okay, first, okay. All right, so first, the positive charge here, okay, and then you can shift the electrons, okay, and then generate kind of another cation, okay, and then further shift here, okay, and then generate kind of the third one, okay. Once you shift here, okay, so you find kind of the positive charge definitely kind of on the carbon with the first nitro group attached, okay. And then this one is kind of extremely unstable, okay, because the nitro group kind of electron withdrawing group, we already know that, okay. They pull electron away from kind of the bending, okay. But now you put the one positive charge on the it's carbon, okay. So that's make kind of extremely unstable, okay. So this one kind of extremely unstable, okay. And then that's the not favored, okay. And the similar thing, okay. So if you want to draw the which quickly draw it, okay. So probably para product, okay. Okay, kind of the para we do this bond. And also you generate kind of three substituent group, okay. Three kind of resonance structures, okay. So right. I just kind of quickly show you guys, okay. Okay, kind of this is meta, okay. So that's wrong structure. Yeah, should open like this way, okay. Right. So goes here, okay, and then you generate kind of the most unstable kind of the resonance structure, okay. Right. So this one, okay, extremely unstable, okay. And certainly kind of you can draw another one, okay. Yeah. So for the both para and also okay, you generate kind of the very unstable resonance structures, okay, put the positive charge on the carbon with the nitro group attached, okay. But if you draw the meta kind of the product, okay, so you won't generate kind of such unstable kind of the substance case, intermediate, okay, we can call it kind of Yeah, positive charge on this carbon, and then you shift carbon, shift here lone pair electrons. Okay. And now positive charge kind of here just bypass here the carbon within nitro first nitro group attached. Okay. And then certainly kind of draw the last one. Okay. So you can see kind of here for the meta substitute kind of here the dinitro compound. Okay, so you never generate kind of this unstable kind of intermediate. Okay, so that's why kind of meta relative has kind of the higher stability compared with kind of ortho and para. Okay, so that's also showed here. Okay, yeah, the two resonance structure form the highly unstable unfavored form. Okay, so that's not favorite forming kind of the ortho and para. Meta will be kind of the preferred. Okay, and so for all in all, okay, so yeah, you guys just remember, okay, so the electron donor group plus kind of hydrogen, okay, so will be kind of also pair reactors. Okay? Electron group kind of except kind of hydrogen will be kind of the electron we call kind of the meta reactors. Okay, all right. All right, here's kind of the full table. Okay, so unfortunately, okay, so yeah, you guys have to memorize the case. So, but actually kind of not hard. Okay, so yeah, just keep in mind all the electron donor group, okay, are kind of also para reactors. Okay, and then hydrogen, although it's kind of deactive group, okay, but it's also para reactors. Okay, and the other kind of electron withdrawal group will be kind of meta reactors. Okay, so that's the not hard kind of memorize the case. All right, okay, so once that's done, okay, so have this a little bit keep in mind, okay, so that's the kind of important thing, kind of one types of the chapter, okay, so one types question you see kind of in this chapter it's kind of ask kind of draw the product for the kind of mono substitute kind of bending, okay, for example, okay, you guys here, okay. All right. So we have kind of benzoic acid try to do nitration reaction for it, okay. All right, and then the nitration group, okay, so where do you put the nitro group, okay? So that's kind of important, the also para or kind of meta directors, okay, for the kind of cascade, okay, so so you for this kind of reaction, okay, so don't look at here, okay, you need to look at kind of what's already on the bending, okay, so this one, okay, determine kind of the nitro group goes, okay, so quite often students kind of look at here, okay, and then where it goes, okay, so that's wrong, okay, so look at here, okay. All right, so nitro group, okay, clearly should be kind of the meta directors, okay, so in this case here the product should like this, okay. Yeah, all right, okay, and now you guys try this question, okay. All right, sulfuric acid, okay, react with kind of the bromo, benzene, okay. So what's product, okay? Okay, so like I said, okay, so look at what's attached, okay, so if it's attached kind of the carbonyl group, okay, or electron withdrawing group, okay, all right, but if attached to the heater atom, okay, nitrogen, oxygen, that will become kind of electron donating group, okay, so no necessary, okay, so the ester has to be kind of electron donating or has to be kind of electron withdrawing, okay, you have to look at what's attachment, okay, what's attachment, okay. Example showed here, okay. Both ester both have kind of the carbonyl group, okay, but you need to look at kind of what's directly attached kind of bonding. Okay, this one carbonyl, this one oxygen. Okay, so that's why this one kind of electron withdrawing group. Okay, this one kind of electron donating group. Okay. All right, so yeah, here's kind of we go back to this question. Okay, so bromine is kind of the hydrogen. Okay, hydrogen we already learned in the previous chapter. In the kind of just the previous slide. Okay. It's kind of also para directors. Okay, so in this case here, when you do the sulfonation, okay, should go to kind of also and para positions. Okay, and then that means kind of for this reaction you should have kind of two product. Okay, one kind of go to kind of also positions. Okay, right. So remember, okay, sulfonation reactions you got kind of SO3H. Okay, that's substitution group. Okay, and then one is go to kind of it's para positions. Okay. Yeah, that's the answer. Okay. All right. Okay. And then in the end, okay. So this class, okay. So try one hard one. Okay. All right. So we have kind of this one we call kind of biphenyl. Okay. Biphenyl compound. Okay. All right. Where is it? Okay. So has nothing to do with kind of sulfuric acid. Okay. Yeah. But yeah, if you like, okay. So yeah, that's here. Okay. Sulfonate group. Okay. But yeah, the real case is kind of this. Okay. Bromine determine kind of where the sulfonate group goes. Okay. Bromine determine kind of sulfonate group. Okay. Right. Okay. Try this question. Okay. So we try to do kind of bromination to this compound. Okay. So yeah, we have to determine kind of where the bromines goes. Okay. Yeah. Once this one done, pretty much. Yeah. Yeah, a lot of students get confused by these questions. Okay, actually, kind of what we can do is kind of treat one bonding as substitute group. Okay, right? So AR. Okay, and then attach kind of another bonding. Okay, and you can see kind of the AR group. Okay, RQ bonding. Okay, actually kind of also para directors. Okay, so that's been kind of the BR should we go here or go here. Okay. But yeah, if you want to put BR here or here, that's fine. Okay, the same thing. Okay, so yeah, pretty much kind of the symmetrical reactions, okay, symmetrical compound. Okay. Yeah, for this one, we also generate kind of two product. Okay. The major should be kind of on the para positions. Okay. And then minor has kind of on also. Okay, because they're kind of stereo hindrance. Okay, stereo hindrance. Okay, so yeah, not easy put on kind of the also positions. Okay. Yeah, so that's the two product. Okay. So in this case, okay, just keep in mind, okay, we treat one kind of bonding as the starting group. Okay, and then yeah, it's determined kind of where its BR goes. Okay. All right, so that's pretty much done the class today. Okay, do you guys have any questions? Okay.